Here is a tiny world with three yes or no facts. A burglary might happen, an earthquake might happen, and an alarm can go off, set ringing by either one. One night, the alarm blares. And the real question is not about the alarm at all. It is, given that ringing, how likely is an actual burglary? In symbols, we want the probability of B true, given a true. That single conditional is a posterior query, and computing it exactly is today's lesson. Before any arithmetic, sort the variables into three roles. The query is what we want to know. Here, the burglary B. The evidence is what we have already seen. The alarm is true, and everything else is hidden. Here, that is just the earthquake E, a variable we neither asked about nor observed. Hidden variables are the ones we must sum away. Now recall what a Bayesian network gives us for free. The full joint over every variable is just the product of the local tables, each node given its parents. For our net that reads probability of B times probability of E times the alarms table given B and E. Three small factors, and from them, we can answer any question we like. The most direct recipe has a blunt name, inference by enumeration. It says the posterior over B, given the evidence, equals some constant alpha, times a sum over every hidden variable of the joint. Read it piece by piece. The sum runs over every possible value of the hidden earthquake, true and false, because to get B alone, we must account for both. And that joint is exactly the product of the network's tables. So expand it. B times E times the alarm table. With the evidence, a true pinned in. Alpha is nothing mysterious. It's simply 1 over the probability of the evidence. The normalizer that makes burglary true and false add up to 1. We'll pin down its value at the end. Let's make it real with numbers. Burglaries are rare, 1 in 100. Earthquakes rarer still, 2 in 100. And the alarm table. It almost always rings for a burglary, sometimes for a quake, and only very rarely on its own. A false alarm probability of 1 in 1,000. Picture the sum as a little tree. The burglary splits into true on the left, false on the right. Under each, the earthquake splits again into true and false. That gives 4 leaves, and each leaf is one product of 3 table entries. The first leaf, burglary and quake both true. O1 times O2 times O95, a tiny 1900 thousandths. The second, burglary true, no quake. Much bigger, about 9 thousandths, since a burglary alone almost always strips the alarm. The third, no burglary, but a quake, about 6 thousandths. And the fourth, neither happened, yet the alarm rang, a rare false alarm, under 1,000th. Now group the leaves by the query. Add the 2 burglary true leaves for the joint of burglary and alarm, 9.4 thousandths. Add the 2 burglary false leaves, about 6.7 thousandths. Their total is the probability of the evidence itself, the chance the alarm rings at all. So alpha, 1 over that, is about 62. Finally, normalize. Divide the burglary true number by the total, and the answer lands. Given that alarm, a burglary is about 0.58 likely. Burglary false is whatever's left to reach 1, about 0.42. And feel the shift. Before the alarm, a burglary was a 1 in 100 worry. That single ring pushed it past a coin flip. Enumeration always works. But look at the cost. The sum has one term for every joint assignment of the hidden variables. With one hidden variable, that's 2 terms. With 10 over 1,000. With n of them, 2 to the n. It explodes exponentially. Worse, enumeration repeats work. Write out the sum, and the burglary term P of B is copied into every branch, recomputed as the tree fans out. On a big network, that redundancy is crippling. The fix is a beautifully simple idea. Do each piece of work once, save the result, and reuse it. That idea is called variable elimination. Here's the trick. In one line. In the enumeration sum, the burglary term does not depend on the earthquake. So there's no reason to keep it trapped inside the sum. Push it out in front. Now only the earthquake terms sit under the sum. Do that inner sum once, collapse it to a small table, and multiply by b afterwards. Pushing sums inward is the whole idea, and it needs one new object, the factor. A factor is nothing but a labeled table, a non-negative number for each combination of its variables. The alarms table, with the evidence A true already pinned in, is a factor over B and E. 4 rows, 4 numbers. Variable elimination works entirely with these little tables. To moves only, multiply factors together, matching on shared variables, and sum one variable out, collapsing its rows. That's the whole toolkit. Let's redo that same burglary query by variable elimination and watch it land on the identical answer with less work. We eliminate the one hidden variable, the earthquake. First, multiply the two factors mentioning it, the earthquake prior and the alarm factor. Now sum out the earthquake, add its two rows for each value of B. That collapses the 4-row table into a 2-row factor over B alone. 9 for auto when B is true, and about 7 thousandths when it's false. Multiply by the burglary prior and normalize, exactly as before. Out comes the same 0.583. But notice, we sum the earthquake out once into a shared table instead of rewalking it in every branch. One more, to see elimination flow along a chain. 4 variables in a line. A drives B, B drives C, C drives D. No evidence. We just want the probability D is true. 3 hidden variables, A, B, and C, all to be summed away. Eliminate a first. Multiply the prior on a by the table for B given A. Then sum A out. What drops out is simply the marginal on B. 38% true. Feed that straight into the next step. Multiply the new B factor by the table for C given B, sum B out, and you get the marginal on C, about 40% true. One more time for C, using the table for D given C, sum C out, and the last hidden variable is gone. What remains is the marginal on D itself, and there's the answer. The probability D is true is 0.3126, about 31%. We never built the full joint over all 4 variables. We just carried a small factor down the chain, one step at a time. A few facts to file. First, elimination and enumeration always agree. Same exact answer. Elimination isn't an approximation. It's just enumeration, organized. Second, the elimination order matters. Every order gives the same result, but a clever one keeps the intermediate tables small, and a poor one lets them balloon. Third, on a nicely shaped network, a polytree with no loops, exact inference is cheap, growing only linearly with the network size. But in the worst case, on a densely tangled network, it's genuinely hard. NP hard, in fact. And that word is our cue for what comes next. Your turn. Rain. R makes the grass wet. W. Rain has a 1 in 5 prior. If it rains, the grass is wet 9 times in 10. Without rain, 2 in 10, a sprinkler say. You walk out, the grass is wet. Pause and find the probability it rained. Here's the walkthrough. There's only one hidden thing. The rain itself, so it's quick. For rain true and wet, 2 tenths times 9 tenths, that's 0.18. For rain falls and wet, 8 tenths times 2 tenths, 0.16. Add them for the probability of wet grass, 0.34. Then divide 0.18 over 0.34, about 0.53. Wet grass makes rain a little more likely than not. If you got that, You've got this. 3 traps to sidestep. 1. You must sum over every hidden assignment, all of them. Skip a value, and the marginal is simply wrong. Don't forget alpha. The summed numbers are unnormalized joints. You must divide by the probability of the evidence, so the answer sums to 1. And 3. Variable elimination is not a different, looser method. It gives the exact same answer as enumeration. It merely reuses shared work, so it's faster. So the whole lesson in 3 lines. To answer a posterior query, sum the joint over the hidden variables and normalize with alpha. That's exact inference. Do it the smart way. Variable elimination. Push the sums inward, multiply factors, and sum out one variable at a time, reusing every table you build. It's exact and fast on loop-free networks, but NP-hard in the tangled general case. And that limit is exactly why. Next, we turn to approximate inference. When the exact sum is too big, we sample instead.